फक्त इंटरनलला टाक. काहीच नाही केलं त्यांचे.
नाही इंटरनल लाईव्ह चालू आहे ना डायरेक्टली.
Automobiles to airspace, semiconductors forms the invisible backbone of innovation. I welcome all the esteemed panel members, all the participants, faculties and students present here. We are truly honored by your gracious presence. With such eminent leaders from academia and industry gathered here, I am sure that today's summit will inspire ideas, ignite innovation, and shape the conversations that lead the semiconductor revolution forward. Before we proceed further, we would like to share that Mr. Raghu Panikar, CEO of Kane Semicon Private Limited, our esteemed chief guest for today's symposium, is unable to join us due to last-minute professional commitments. We extend our best wishes to him and look forward to his presence at future event. We now take a moment to honor our distinguished guest from Kane Semicon Private Limited, whose presence adds the immense value to this event. I request our Honorable Vice Chancellor, Professor Manish Bhalla sir, to felicitate our chief guest, Mr. Paul Ilangovan, Head of Operations, Kane Semicon Private Limited. Mr. Paul is a distinguished semiconductor packaging expert with over 30 years of industry experience. He has led major operations across organizations such as Kane Semicon Private Limited, Tata Semiconductor, and Sahasra Semiconductors Private Limited, with expertise in IC packaging, manufacturing, and operational excellence. We are delighted to have you, sir, with us today. Thank you, sir. I request our Vice Chancellor, sir, to felicitate Dr. Basant Saini, Senior Engineer, R&D, Kane Semicon Private Limited. Dr. Basant is a specialist in advanced semiconductor packaging with expertise spanning device modeling, clean room fabrication, wafer level characterization, and OSAT-based package development. His work covers next generation packaging technologies including QFN, QFP, CSP, BGA, and many more. Before joining industry, he serves as a senior research scientist at IIT Bombay. We are delighted to have you, sir. I also request our Honorable Vice Chancellor, sir, to felicitate Mr. Saif Alam, Program Manager, Kane Semicon Private Limited. Mr. Saif Alam is a semiconductor policy and project management professional at Kane Semicon Private Limited, working at the intersection of technology, governance, and large-scale program execution. With over a decade of experience across India and the Middle East, he plays a key role in aligning semiconductor initiatives with national programs such as India Semiconductor Mission. He specializes in regulatory compliance, initiative management, and government liaison, contributing to the successful execution of high-impact semiconductor projects. Thank you so much, Honorable VC sir. You can take your seat. So friends, it is now my honor to invite Dr. Mrs. Anupama Patil, Dean, Faculty of Engineering and Director, SEMR, DYPIU, to deliver the welcome address.
Very good morning, all the dignitaries on and off the dais. Today, chief guest, Mr. Paul, Mr. Basant Saini, Mr. Saif Alam from Kane Semicon, distinguished speakers, respected panelists, industry experts, faculty, and my dear students. On behalf of Faculty of Engineering, D.Y. Patil International University, it is my privilege to extend a warm welcome to all of you to this Semiconductor Symposium. We are honored to host such an eminent gathering of experts and thought leaders who are shaping the future of this critical domain. The ongoing global focus on chip manufacturing, supply chain resilience, and advanced packaging highlights how strategic and essential this sector has become for national growth and technological advancement. As all of you are aware of the India's semiconductor mission, India is now at the pivotal moment with strong policy support and increasing industry participation aimed at building a robust semiconductor ecosystem. This creates immense opportunities for academia to contribute through creating a skilled manpower, research, and innovation. As an academic institution, we at D.Y. Patil International University recognize our responsibility to prepare engineers who are not only technically proficient, but also industry ready and innovation driven. Today's symposium has been thoughtfully designed to reflect these priorities. We are privileged to have a keynote address by our esteemed chief guest, which will set the vision for the discussions ahead. In addition, we'll have the technical talk focusing on specialized areas, and engaging panel discussions will bring together diverse perspectives from academia and industry. Such platforms of symposium are essential for bridging the gap between theory and practice, fostering collaborations and inspiring new ideas that can drive the semiconductor ecosystem of India forward. I extend my sincere gratitude to all our speakers and panelists for their valuable presence and contributions. I also congratulate the organizing team of Department of Semiconductor Engineering for their dedicated efforts in bringing this semiconductor event live. I encourage all participants, especially our students of engineering, to actively engage, ask questions, be curious, and make the most of this opportunity to learn from these leaders of the field of semiconductor. Once again, I warmly welcome all of you and wish you a highly informative and impactful symposium ahead. Thank you very much, all of you.
Thank you so much, ma'am, for your inspiring words. To give us an overview of today's summit, I now invite Dr. Priya Charles, Associate Director, SEMR and Head, Department of Semiconductor Engineering, DYPIU, to brief us about the program.
Very good morning, all of you. Good morning to all the distinguished dignitaries, respected delegates, esteemed industry leaders, academicians, and my dear students. It is indeed a privilege and a great pride of moment for me to welcome you all to the Semiconductor Technology Leadership Summit 2026 at D.Y. Patil International University, Pune. Today, we gather at a time when the semiconductor industry, it is not just an enabler, but the very backbone of global technological and advancement. In recent years, we have also witnessed how the global semiconductor landscape is evolving rapidly, with nations placing strategic emphasis on building resilient and self-reliant supply chains. India, too, is taking significant strides in this direction, creating unprecedented opportunities for talent, research, and innovation in this domain. At D.Y. Patil International University, we recognize this transformative shift and have taken a proactive step through our BTech Semiconductor Engineering program. Our vision is not just to educate, but to empower, to create industry-ready engineers who can contribute meaningfully from day one. One of our key strengths is our focus on experiential learning. With our state-of-art fabrication laboratories, Silicon Forge, and the clean room facilities that we have in the lab, we are providing our students with the rare opportunity to engage directly with semiconductor processes. This hands-on exposure is critically in bridging the long-standing gap between the academic knowledge and industry expectations. So this symposium has been thoughtfully conceptualized as a platform for dialogue, collaborations, and inspiration. By bringing together leaders from academia, industry experts, and research professionals, we aim to create an ecosystem where ideas are exchanged, perspectives are broadened, and meaningful collaborations are initiated. I'm particularly delighted to see the overwhelming response for this event. The presence of all the representatives here today reflects a shared commitment towards nurturing talent and strengthening India's position in the global semiconductor arena. While we were eagerly looking forward to hosting Mr. Raghupanikar, the CEO of Kane Semicon, and though he could not join us today due to some unavoidable commitments, we remain grateful for his continued support and encouragement to DYPIU towards this initiative. Nevertheless, he has sent his great team. Thanks a lot for that. I'm confident that today's session will be insightful and enriching. More importantly, I hope this symposium serves as a stepping stone for long-term collaborations, knowledge exchange, and innovation-driven partnerships. Once again, I extend my heartfelt welcome to each one of you and thank you for being a part of this important initiative. Let us make this symposium a truly meaningful and impactful experience. Thank you.
Thank you, ma'am, for setting a clear and inspiring direction of today's event. We are privileged to have with us a visionary leader whose constant encouragement fosters innovation and excellence at every level. It is my honor to invite Honorable Vice Chancellor, Professor Dr. Manish Bhalla, sir, to address the gathering.
Good morning. Invited guests on the dais and off the dais, dear faculty members and dearest students of DYPIU. I want all the students to raise their hands, those who belongs to the semiconductor branch. Yeah, most of them are from the semiconductor. Thank you. Well, today is the function or event, you can say, that gives a strong platform to all of you to interact the leaderships, particularly in the semiconductor field, and share the ideas, your innovative ideas, and they will respond. Today, while interacting our invited guest in the boardroom, I got to know that there are government policy on the semiconductor mission of India. So I want every student to take it very seriously and just read the policy of the semiconductor mission of India. Every student has to understand, because the semiconductor is the need of the hour in order to India to be self-reliant. And all of you being in the semiconductor branch, you are going to lead the nation. So by that way, you have to have the policy in your mind, and by that policy you can frame your path, future path, accordingly in order to sustain you in this particular field. This initiative was taken away back, I think, 2 years back, and we have created a state-of-art semiconductor lab, a fabrication lab, and I interacted in the morning that we have a vision to expand this particular semiconductor lab or the Silicon Forge lab in the second phase, whereas we have already earmarked the space for the packaging part. So in totality, your expertise in the semiconductor field will result a very good outcome, and also first in the nation as a state private university to have this particular Silicon Forge lab. in DYPIU. I also reiterate to all the students and to our faculties to go for sustainable this lab, because we have to sustain ourselves. All the time, DYPIU will not make give the inputs on terms of the financials to sustain the lab in a good manner. Wherever it was established in various IITs and other organizations, central organizations, the sustainability is the important thing. And being a private sector, you have to sustain your lab, to sustain your lab and maintain the lab. So I reiterate to all the students, I request to all the students that consultancy and the grants from the government in order to do the research at the UG level, because DYPIU has implemented a undergraduate research policy in order to strengthen the research ecosystem in DYPIU. And we are sharing to our experts that right now around 20 odd research projects from the research undergraduate research society the students have submitted with the mentors for the sake of research and development. So create the innovative ideas by your innovative thinkings, and with the consultancy you will sustain your labs. I think this summit, leadership summit, will benefit you, and the experts, the kind of experts we have invited through various collaborations, particularly Keynes. I think it will give a very...
Ma'am Indira Gandhi, we have established semiconductor lab in Mohali. That was the first one in 1970s. But unfortunately, that plant was completely destroyed in a fire accident. As of today, nobody knows what was the reason behind that. Again, later, after some time, the same semiconductor lab was established, but not in a full momentum at the time. Things going on. Then in 1987, there was a company in South, in Chennai. They have started a semiconductor company, which is called Spell Semiconductor. I was happy to be associated with that company for 21 years. That was the first commercial semiconductor organization in India. They have manufactured all the legacy packages. It was a 100% export-oriented unit. So in 70s and 80s, India already started in the semiconductor, but unfortunately, we were lagging in expose ourselves to the world. That was a major issue. But later, under Dr. Manmohan Singh, India plans to sign 2 MOU for wafer fabs in India. But again, unfortunately, that also didn't happen. But at the time, they have formulated so many incentive schemes called MCIPs and all those. So they put the base for semiconductors at the time. Then during our current Prime Minister Modi ji's period, it gets accelerated. Now we see that there are 10 semiconductors companies approved under ISM scheme till date. In the first scheme, the government has allocated 76,000 crores in the first batch, under which all the 10 companies approved. In the recent budget, our government has allocated 40,000 crores to establish the ecosystem. Because once we set up the semiconductor field in India, as of today, all the raw materials, all the equipments, we have to depend on the overseas. All are imported. So to develop that ecosystem, this ISM 2.0 will help us. So this is the story in India about semiconductors, because majority are you in semiconductor branch. It will be good to know about this history. So why semiconductor? If you can see in this hall or in your hand, whatever you have, everything has semiconductor, right? So whether it is a mobile or the lights or the LEDs, whatever it may be. So it is semiconductor. So in India, semiconductor will be the near future, which means no semiconductors, no digital economy. So India, as of now, it is 18% producing the semiconductors compared to China. China, it is 82%. So India has a very good potential where you guys have a very good market. So last week I was there in another university in Vadodara where they don't know about this semiconductor market in India. So when I explained them about these opportunities, they were very much happy and they plan to visit us on 24th, day after tomorrow this week, because they also want to collaborate with us. Because they know now that semiconductor will be the driven force or driving force for the Indian economy as well as for the youth. So I request you all to focus on all your studies because there are plenty of opportunities. So when there is a concept that converted into a chip, there are so many aspects involved in that. First thing is that concept to be converted into design. So in semiconductors, we need design engineers where you can get that opportunity. Design verification, IP, there are plenty of verticals in under design. Then the design converted into a wafer, which means the silicon or silicon carbide or gallium nitride. So that is we call as a front end, wafer fab. We have seen your facility. It's a really amazing thing. I congratulate all the professors who work on this. So you people have a wonderful setup here on the wafer fabrication level. Then the next is that wafer will be converted into a package, the desired package. There are so many packages, legacy packages like, surface mount devices or through-hole packages, ball grid arrays, flip chips, wafer level chip scale packages. There are plenty of packages available. Keynes involving in that activities. We are doing the packaging and final electrical test. So this is the life of the semicon. Then this chip goes into the PCB, whatever be the design and all those things. So you have plenty of opportunities in design or in the fab or in the manufacturing or the packaging industry. So the semiconductor packaging is a very complex process, not as easy as that of other packages or other process. So there are 13 to 15 processes involved in this activity. So you have a huge opportunity to learn further and to develop you, whereas your development will help to the Indian economy to grow as well. So there is expected that the semiconductor market will be $1 trillion in 2030. That is the estimated value, where you are having so many opportunities. And in fact, our government is really helping us to develop this because they are introducing the various schemes like under ISM. There are production link scheme, PLI, and design linked incentives, DLI. There are plenty of things to develop. As VC sir mentioned, so they are helping us to the academic institutions also to develop this. So when we consider the global semiconductor market, as you well aware that due to the geopolitical issues, many of the semiconductor companies, they are moving out of China. All the companies, the next destiny, they look at India. So that's why we are having a huge opportunity and 10 companies are signed off. When I discussed with the ISM CEO, he mentioned that there are plenty of other applications are there which are under scrutiny. So we expect that there are more semiconductors companies will be here. So this semiconductor indirectly will help us to grow the artificial intelligence, the EVs. Nowadays you can see the EV market is keep on growing. Even in India is pretty much growing, almost double to triple. You can see Tata Motors, there are 8 EV vehicles are under testing now. Similarly with Mahindra also. So everyone is looking into the EV vehicles where there are plenty of semiconductor devices will be there. Then we will have IoTs and 5G and beyond. Now 6G is introduced. So everywhere, semicon is there. So in this scenario, where India can play, that is the question. You can say there are opportunities are there, but how India can play into that? So we can say that, as I mentioned, chip design and innovation, which is very critical. That's why in Keynes Semicon, we have a separate R&D team. Dr. Basant is one among them. All our R&D team members are from IIT scholars, PhDs. There are 10 to 11 people, because we feel that R&D is a key factor in any semicon industry, where you will also play into that. So India already have a very good base on design. You can see that in Bangalore, Hyderabad and Pune also, there are plenty of design centers there. So we can further elevate that with the support of the youngsters. Next, we can have the compound semiconductors. As of today, India's packaging capability or capacity is very much less, where we can accelerate that with all the 10 companies. 10 companies are the packaging company. There is one fab, which is under Tata's brand, comes in Dholera. So once the fab in 2028, it is expected to be rolled out. When it comes, the complete ecosystem will be here. At Keynes Semicon, we are focusing more on power module packages, whereas Micron is on the memory side, and Tata's, they are into their own, Tata has all their factories where they plan to produce their own ICs, whereas CG Semi, which is our neighbor company, they are already having a tie-up with Renesas, where they produce the industrial and automotive ICs. So each of us have a different thought process and different product, where we should not compete with each other. We have our own roadmap. In fact, our team is working on advanced packages. Perhaps during the panel discussion, Dr. Basant can highlight some of them. We are working on co-optic packages, which is a very new one. We have already tied up with couple of US companies, and we are in discussion. Similarly, on other 3D glass, silicon via, that kind of advanced packages we are working, because R&D, the design is very important. So second thing is on the compound semiconductors, where we can accelerate the throughputs, where we can export and we can meet our own requirement. You know that the semiconductor import is as equal as to our oil import. I think it is more than that, based on the studies. Now we have a very crucial time for the oil. Similarly, soon that may happen for the semiconductors also. So we should stand on our own. That's why the government is push. In fact, government has set a target to each of this industry, so that we should meet the target. We should produce something. I think many of you know that on March 31st, our Honorable Prime Minister inaugurated our unit, and our commercial production started. So in such a way, the previous month, February 28th, he was there in the same area to inaugurate Micron facility. So the minister, he is keep on in touch with us through ISM. What is the progress? What is the, how many units been produced? So the government is full focus on this semiconductor industry now, because there are plenty of need for our own industries. Then automotive and industrial electronics, which can be, elevated into next level. As I mentioned that EV is one among them. Similarly, there are plenty of other activities. Normally, in one advanced car, more than 200 plus chips used for various applications. So this can be increased to 500 as per the studies. Everything is controlled by the semiconductors. So which is, we can say that it's kind of oxygen now. And most importantly, India can lead, because India has more youngsters compared to rest of the world. You know, in Japan or in the European countries, the youngsters ratio is going down because people does not want to marry. They want to enjoy the life. The same scenario recently started in India. I don't know. You are all Gen Z kids. So you want to live your life enjoyably, but that's not the case. If a country has to grow, it has to have plenty of youngsters. Fortunately, India has that. So India can lead the world in terms of semiconductor with your support. The next point, what we discussed this morning, is that the importance of academia and the industry collaborations. Because recently I have the opportunity to visit so many colleges. Even after 33 years of my study, I was fortunate to deliver a keynote address in my own college where I studied. So when I meet all the professors, one thing I noticed that in their mind, they think semiconductor is just a VLSI design. It is not that. So beyond VLSI, there are other verticals also in semiconductors. So my humble request to the professors, first you have to learn, or you have to educate yourself on this semiconductor. That is important. How that will happen? That will happen with the industry collaborations. Because we don't say that we are masters in that, but at least we can give some tips to you. We can bring you to the world, the actual world, because the theory versus practical is completely different. The students who are learned in the classroom won't help 100% when they come to the floor. So that's why the academia and industry collaboration is very important. And we are very much happy that Kane Semicon has a MOU with DY Patil, and we are already closely working with them. And this morning I promised VC sir that we will help you to set up the back end, the packaging line also, and the same on the recruitment side also, because we need plenty of talent pool. What has happened, right? Since we don't have this much, we have recruited people from Philippines, Malaysia, and Singapore. Not only Keynes, all the other companies also. When we have a huge talent, the youngsters in India, why should we depend on other foreign countries? So that is a big question. So the academic institutions should have industry collaborations where industry will help you out to train the students, to form the curriculum, and to give the inputs to the professors also. So which gives you the practical knowledge, because your students can visit our facility where they can train at least a week so that they can know what it is. They will immediately compare to their studies, what they have taught or what they have studied and versus the actuals. Then it may help us to do the final deep dive into that particular subject. So that is important. And they may have a cross-disciplinary thinking. Just now, when we enter into the lift, me and ma'am has discussed who are all the participants in that. She mentioned other than civil. But I told her, why not civil? Because constructing a clean room for a semiconductor industry, civil is very important. They should know what is a clean room, what is 10K, what is 100K cleanliness. So every department is important in semiconductor, whether it is mechanical or mechatronics, civil, chemical, because why you do chemical is needed. In semiconductors, we have a electroplating line. In the front of the fab, everything is chemical. So chemical engineers is needed. Similarly, electronics. So all curriculum functions or departments is important to us. So I wish all the students to communicate this among your friends to focus on these activities. So I don't want to take too much of time, but semiconductor, as I mentioned, it is a very complex process. You have to have patience. All individual process is unique and very complicated, where you have to learn a lot before you act. So learning is important. So you have to have such patience to learn. Next is precision. because semiconductor is working on micron level thing. You can see the wires, whether it is gold wire or copper wire that we use, is thinner than our hair. So the precision is very important. When you do the connections, the bond connections or the ball connections, precision is very important. So you should have that precision, that talent. Next is continuous learning. As I mentioned, just we started with the legacy packages. Now we keep on moving to the advanced packages. Based on the market requirement, the packages or the technology will get improved, and you have to have the capability or the interest to learn continuously. That is the other key point. Then strong fundamental. So the theory is seriously is needed. That's why we have recruited all the PhD scholars for our R&D team, because theory is important. So you have to have a strong fundamentals. So all of us, we know that we have two eyes, to see, to observe, to understand. Similarly, as a students, you should have two eyes. I would say, first eye is the interest, second eye is involvement. If you have these two eyes, you will definitely come up in the life, and in front of you, you have a very good opportunity called semiconductor, and I wish the management who has taken the very courageous step to introduce this program here, where there are plenty of students already registered and learn. So I wish you all the good luck to the management and to the students. And once again, I thank you, the management, for inviting me to be here. And I wish you good luck. Thank you.
Thank you, sir, for your truly insightful and inspiring address. Your words have given us valuable perspectives of the evolving semiconductor landscape. Before we move ahead with the felicitation of our esteemed panel members, may I take a moment to request our respected dignitaries to kindly take their seats in their front row as we move on to the next segment of the program. At the same time, I humbly request our Registrar Sir, Madhvi ma'am and A.V. Patil ma'am to graciously remain on the dais and do us the honor of felicitating our panel member. May I also request Dr. Basant Saini sir to please remain on the dais as he continues with us as a part of the panel. And now, ladies and gentlemen, it is time to honor the distinguished minds who will be leading today's panel discussion, leaders whose expertise, innovation, and vision continue to shape the future of India's semiconductor landscape. Guiding today's panel discussion, may I call upon an esteemed academician and leader, Dr. Arvind Shaligram, CEO of SPPU Research Park Foundation, who is also the moderator of today's panel discussion. I request Dr. Miran Moidin sir to felicitate Dr. Arvind Shaligram sir. Dr. Shaligram is a distinguished figure in the field of electronics and semiconductor research, known for his contribution to academia, innovation, and industry collaboration. As the CEO of SPPU Research Park Foundation, he plays a pivotal role in fostering research-driven innovation, startup incubation, and industry-academia partnership. With decades of experience in teaching, research, and leadership, he has been instrumental in nurturing talent and advancing technological ecosystems. Sir, we are truly honored to have you as the moderator for this session. I now call upon our next distinguished panelist, Dr. Ashwini Agarwal sir, a highly respected leader in India's semiconductor and electronic ecosystem. May I request Dr. Miran Moidin sir to kindly felicitate Dr. Ashwini Agarwal sir. Dr. Agarwal is a fellow of India Institute of Electronics and Telecom Engineers and IEEE senior member and the founder chair of the IEEE EPS Delhi chapter. Dr. Agarwal currently serves as the chair of the Semiconductor Skill Committee at the Electronic Sector Skill Council of India, where he plays a key role in shaping national skill standards for the semiconductor domain. With over 4 decades of distinguished experience, he has held leadership roles including Director of Government Affairs at Applied Materials India, contributing significantly to public policy strategic programs and the industry developments in semiconductors. He is also a professor of practice at Manav Rachna International Institute of Research and Studies, a true stalwart of the ESDM ecosystem. Thank you, Dr. Biran Moidin, sir. I call upon next distinguished panelist, Mr. Kedar Patankar, a multifaceted semiconductor executive, award-winning writer, heritage steward, and 2-time TEDx speaker. May I request Dr. Madhvi Deshpande ma'am to kindly felicitate Mr. Kedar Patankar, sir. Mr. Patankar holds a B in Instrumentation and Control Systems from Mumbai and dual master's degrees, an MS in Electrical Engineering and Computer Science and an MS in Management of Technology, both from the University of Minnesota. He spent nearly 20 years in United States shaping deep expertise across the semiconductor industry. His professional journey includes significant roles in ASIC and chip design domain, having worked with leading global companies such as LSI Corporation, Avago Technologies, Broadcom, and later at Seagate Technology at the product level. In recent years, he has served as CTO, consultant, and business head for semiconductor startup including P2F Semi, SIGPT, leading initiatives in chip design, AI/ML, embedded systems, and custom ASIC development. Alongside his engineering accomplishments, Mr. Patankar is an award-winning professional 24. His contributions extend to education and heritage stewardship, from advising academic boards at leading institutes to spearheading food cleaning drives, a rare blend of technologist, storyteller, and social contributor. Now I call on operation and building high-impact team across the semiconductor value chain. He has held leadership positions including Associate Director, VLSI Design at TESOL and Chief Operating Officer at P2F Semi, during which the semiconductor division successfully transitioned to TESOL. Mr. Yevle is also the founder of MB5 Technologies and co-founder of Tech School, ventures that have contributed significantly to embedded product developments and VLSI skill building. May I invite our next distinguished panelist, Mr. Bhairav Shah, founder and CTO of Parshvanath Robotics Pune and Group Head of Semiconductor Ecosystem Development Initiative at MCCIA. I request our Director, A.V. Patil ma'am, to felicitate Mr. Bhairav Shah. Mr. Bhairav Shah is an international award-winning robotics innovator and a passionate electronics engineer. He brings over 12 years of experience across industrial research, product development, and entrepreneurship. He is widely recognized for his contributions to innovation, including being an inventor of light fidelity and for developing over 50 special purpose machines. He is currently engaged in the development of semiconductor ATMP equipment, contributing to India's growing capabilities in semiconductor manufacturing, a dynamic innovator and technology leader. I thank our dignitaries, Dr. Biran Moidin sir, Dr. Madhvi Deshpande ma'am, and A.V. Patil ma'am. And now, I warmly invite our moderator, Dr. Arvind Shaligram sir, to kindly take the lead and guide us into the panel discussion.
Good morning, everybody. It is an honor for me to be moderator for such elite panel. And in fact, the subject itself, the semiconductor technology and semiconductor roadmap, is very much significant and very much important, as it happens to be in the third decade of 21st century. Because for years together, we have been talking about what will be the 21st century technologies. Now we have already crossed the 21st century barrier and we are in the third decade. We realize that there are so many things which have happened, and these things, they are essentially governed to say that they are governed by Moore's law. Gordon Moore, who was essentially the visionary in 1965, predicted some kind of growth, some growth curve, maybe doubling of the device count and reducing the size of the devices and say increasing the performance levels and so on. So variety of things he suggested, but subsequently what we realized that it is the technocrats all across the world, they have contributed significantly to make that particular Moore's law valid. It was just one statement he made at one point of time, but it was basically because of the millions and billions of people who have significantly contributed in the development of the technology, and not just the technology, but even the business growth. Because the other aspect of it, like why the semiconductor technology is so popular, is basically there are so many users. And the users, they contribute in the growth of the semiconductor demand. It is demand driven. So I think in today's panel discussion, we will touch upon variety of aspects which are associated with the semiconductor technology. We know that initially semiconductor meant silicon and germanium. Subsequently, germanium took the back seat. Silicon progressed further and further. The people talked about silicon technology reaching to the end of its physical limits by 2020. We have also well past 2020 now. And we know that there are a variety of other semiconductors which have essentially come into the play along the path. They include various kinds of compound semiconductors. Initially, LED technologies, they were driven by some, say, germanium or some compound semiconductors like AlGas. Now, we see that the AlGas technology has taken the back seat, and we have the silicon nitride as the technology, germanium nitride as the technology, which is essentially coming into play. And we have not just only the semiconductors which are in the single crystal form, but the semiconductors in the form of organic semiconductors. They are playing key role in the advancement of the technology. So we have such wide canvas of the semiconductor technology in terms of semiconductors per se, and the applications are tremendously expanding. So the panel, we have very strong panel, and they include in them a big experience, and the experience essentially is on different aspects. So I think we'll have a format wherein I'll just raise some questions, and probably they'll answer, as well as they'll elaborate on their own contributions in the domain. So I think we'll begin. Here people are from different domain, the experts. The first question that I'll ask to Mr. Ranjit Yavle, who has a very strong experience in terms of the technology and technology initiatives related to the startups and so on. So my question is that how semiconductors act as the backbone for the next generation technologies such as AI, 5G, 6G, and quantum computing.
Yeah. Thank you, sir. So, good morning, everybody. Semiconductor typically is a very huge field. And fortunately, when we started our career, we didn't have too many options, but whatever options we had, we could look at how a lot of EDA tool development was done, how it was probably used in designing a lot of complex chips and so on. So with my experience, and probably the panelists here will agree that with the evolving and the emerging technologies like AI and ML and deep learning, the core importance of semiconductor now is able to be like a common household term, which probably in early 2000 was still a what do you say, access of very few or limited engineering resources. So probably you guys are very fortunate now that semiconductor has become a household term, but that also gives us the opportunity to work on so many initiatives, and probably providing the clean room here in D.Y. Patil University. Probably we heard it's like first of its kind. We have that opportunity to really make a huge difference in this industry. Yeah, and I don't have to pinpoint at things. Whatever we see today is all about semiconductor, and then with emerging technology, it makes more sense to make that semiconductor technology or the chips what we are working on more faster, more reliable, more low power, efficiently working on performance and so on and so forth. So if you ask me, huge opportunity for all of you. Just make sure you got your fundamentals right. Work on your basics. Make sure you choose the right path in developing. Because I'll tell you from my experience, probably pursuing your career and what you actually want to do are parallel tracks. So eventually you will figure it out. But as a panelist today, I just want to make sure and give you that message that this field is here to stay, because even in early 2000s, we were told this is a very niche industry and we don't know what's the future of this industry. And but it's here to stay. Even Moore's law has been there, will be there. And with emerging technologies, it makes more sense to focus on semiconductor design as well as manufacturing. So yeah, to just answer that question, semiconductor is the backbone of any emerging technology, because if there is no hardware, you cannot run stuff. So yeah, thank you.
Very well said, that semiconductor technology is at the backbone, and as normally the backbone is not seen, but it exists, and because of that only we can work, we can stand, we can sit, and so on. So semiconductor technology, the chips, they are at the back of every application, new application that emerges out. My next question is to Dr. Vivek Kumar. It is interesting to note that over the years, the technology has been essentially growing at a very rapid rate. And there are different trends which have emerged in the applications domain as well as in the selection of the materials and so on. So what are the key global trends shaping the semiconductor industry role in future technologies?
Thank you, sir, for the nice question. Good morning, everyone. That global trends which are shaping the semiconductor industry future. So this is very obvious question. Ki why semiconductor is so much famous? Our country, USA, China, all European Union, almost all country, you will see after the COVID, they are running behind it. So there is the obvious reason. So if you will look around, you will find the answer. So around us, you will see mobile phones. Earlier, mobile phones were 2G, 3G, 4G. Now we have the 5G. And we are expecting 6G maybe in upcoming few years. You will see the cars. earlier the conventional car, there is no like big screen in the car, sensing, like no car are EV, autonomous car already launched, right? So if you will compare, first let us take the example of mobile phone. If you will go from 2G to 3G, I think you all can remember when you shifted from 4G to 5G, you changed your phone, right? When why we changed the phone? Only technology changed, right? Technology. If you are changing the 4G to 5G, the internet speed is increased exponentially, right? If you will go, it's in the gigahertz. If you will go from 5G to 6G, it's around more than 200 or 300 gigahertz. So only changing the transmission system, or like, you have to change your mobile phone. And mobile phones, what are changing inside that? That is the processor, which is going to process the 6G signal or 5G signal. So if you are shifting from 4G to 5G, earlier device has the expected 1 million transistor, same mobile phone. Now same mobile phone have the more than 100 million transistors. So if you will talk about the cars, nowadays cars have more than 100, 200 chips. Everything is like, if your system will not work, your car is not going to start. You have the smart. You want a smart car. Everyone want to the high end of the car, like EV. EV had the 4 or 5 times larger number of chips compared to the conventional cars. So another famous terms we are aware as a teacher or a student, we all know, that is the ChatGPT. Okay, we all are using, teachers are very much worried how to evaluate because students are using frequently in their assignment and classes. ChatGPT, if you will observe that ChatGPT 1, 2, 3, 4, DeepSeek, that's I think from the China side, right? So these all are the AI. So how they, this AI algorithm were developed in 1960s, right? 60s, 70s, if you will find the papers, you will find that. But why they suddenly famous in 2024 or 23? Reason was the advanced GPUs, chips, semiconductor chips. If you will see your watch, now watch is the smart watch. It can sense your EEG signal, ECG signal, ECG signal. It will transmit to the mobile phone. It will give you the weekly report. So if you will look around, every instrument is becoming smarter day by day, right? So if these all instrument, either biomedical, if you will AI, if you will see EV, like cars, mobile phones, they all work on the 3 principles: sense, process, and communicate. Sense, like your watch, a smart watch is going to sense your like heart, your sense, your pulse rate, and then it is going to process, and then it will send to the mobile phone. So for sensing, for processing, and for communicating, only one thing is required, that is the semiconductor. That is the semiconductor chips. One thing is common behind the all is the semiconductor. Okay, this was the explosion of application which is leading the semiconductor industry, because we want, if 6G technology will come, everyone will run behind that. We want a like car have with the big screen, all features should be there. So what is the behind that? That is the semiconductor. This was the in terms of application. Another, if you will see, during the COVID, few foundry, I think in the world we have very few TCMC in the Taiwan global foundry. 90% chip is fabricated by the TSMC. So during the COVID, foundry were not working, operations were disrupted. So it affected directly to the car manufacturer. Car manufacturing was stopped, and it was, I think, in 2021, all country felt that if we will dependent for only one country, that is the Taiwan. We know in the current situation, a state of Hormuz condition, right? So why we are facing the oil crisis, gas crisis? That is the dependency. So if our dependency will be on a single country, so in the future, if any blockade around Taiwan will be there, it is going to stop our all industry, including automotive, biomedical, mobile phones, everything. So after 2021 USA by Chip Act, our Honorable Prime Minister they already launched Indian Semiconductor Mission to establish we already have a well-established design system. He focused on the fabrication part. So we can see, as a strategic point of view, if one country they can stop our all industry, only stopping the semiconductor chip coming out from the TSMC. So all countries are now focusing towards developing their own ecosystem of the chip fabrication. So nowadays, semiconductor or MOSFET is not a single component. This is the technology which is driving the future. So without semiconductor, you can't expect like your car, your mobile phone nowadays. So this is my answer, why semiconductor leading the like future technology. If you will say that there is the quantum computing, no, quantum computing required the classical computer to show the answer. So there is the cryo CMOS concept is there. That is again the silicon. You suddenly can't change the complete ecosystem of the silicon. So silicon is driving the all technology. Okay, thank you. Thank you so much.
Very well said. Silicon is the real estate, and this real estate essentially has to be properly managed. So for managing the real estate, we look at like a complete ecosystem to be built around semiconductors, because semiconductors are not just the ones which are to be studied in the curricula or the ones which are to be practiced in the laboratories, but these have to be manufactured in the factories, and just manufacturing is not enough. It has to be sold in the market. India is one of the major markets in the global scenario. So I think my next question to Dr. Ashwini Agrawal, who is chairman of Semiconductor Skill Committee of India. So I'll just like to ask the question, how can countries like India build resilient semiconductor ecosystem to support emerging technology innovations?
Thank you, Arvindji. Friends, I want to give a contrarian view. Resilient semiconductor ecosystem is not built. It is not built. It is actually orchestrated by creating music for a target market that you want to actually aim for. Okay? You start with the customer, you will never go wrong. So start with that customer. And then you put in place a few frames. There are 4 frames that shape this ecosystem. And that is, the first one is the fabless. So the VLSI engineers here will have a play definitely to bring those chips designed for that particular target market. You also look at the manufacturing piece, which means you need the front-end manufacturing, and you have a lovely lab that has been created here. You will need the ATMP or the packaging setup, okay? And then you need the other related, setups for manufacturing to create that particular ecosystem. You need the supply chain. That's the third frame, third part of the frame. And lastly, you need talent. You need to scale up skills by an order of magnitude. See, we can import chips. We can't import competence. That's what Paul Ji had mentioned. You have people coming from everywhere into all these companies, but that's not a sustainable model. So if you want a resilient, sustainable model, you need to actually selectively look at creating the India story on it. And definitely talent is one of them. Okay, literally look at it like this. Talent is the only node in semiconductor manufacturing. Okay, it is that doesn't shrink. Okay, it is a key part of the Moore's law. So we actually need to look at that. To create that sustained resilient ecosystem, you need to move from the investment-based entry actually to capability-based sustainability. And I think that's That's the path to it. So at Electronic Sector Skill Council, where I am involved with the National Occupation Standards, we try and take a look at the talent piece in depth, and we'll talk of it subsequently. But clearly, we need to actually look at what is really required by the industry and make sure that there's a convergence between what is being delivered at the institutes with what the industry needs. So,
Thank you. It was a very important insight that you have given. My next question is to Mr. Kedar Patankar. How are advancements in semiconductor nodes? Because we know that semiconductor nodes are shrinking by very big factors. Like we are now in the sub-nanometer, sub-5 nanometer kind of region. And this advancement is continuing. So how these are influencing the performance of next-gen applications?
Yeah, thank you, sir. Thank you all. So like sir is saying, we are at like 2 nanometer or 3 nanometer. And in last 20 years, we have gone down from 180 nanometer to 2 nanometer. Now everybody is referring to Moore's law, and like somebody said, Moore's law sort of became a self-fulfilling prophecy for the industry. So everybody wanted to fulfill Moore's law, right? So while we are working on one technology node, these companies would announce, oh, we have the next technology node coming up, and foundries and all that, right? And so 28 nanometer, I remember 28 nanometer was one of those nodes which was pretty stable. It was pretty good in terms of yield, in terms of power, in terms of performance. But the company still kept, going deeper submicron, more than 28 nanometer. And so then the debate became about what is the trade-off, right? Because how fast really you want to be, or how small you want to be, versus how much money you want to spend on EDA tools or manufacturing, right? So that's a trade-off, and that was a conversation at the time. And I remember that at one point of time, it almost seemed like Moore's law wasn't useful anymore, because the cost of doing those submicron chips was so high that it doesn't make sense for all the products. But I think that whole paradigm got shifted because of AI/ML, and AI/ML brought in so much need for compute, right? And obviously we know that for AI/ML or ML to work, we have multiple chips, and we have model parallelism and data parallelism. But still, on one single chip, there is an immense need for compute. And so what that means is that you have to pack millions and millions of gates in one chip. With older node, 28, it's not possible. So you have to go deeper submicron. So with 2 nanometer, 3 nanometer, we are able to get there where we are able to pack so many gates, so many transistors, millions of them in one single chip. Now, while they did that, they also changed the transistor technology, right? So they went from planar to FinFET to now gate all around, GAA. With that, what they did was they got a better control, better electrostatic control, and so they could control the leakage. So now if you think about it, once you control the leakage, those kind of chips can go in edge applications which are battery powered, right? So you don't want leakage to happen. So they got, hold of that. Then there are other methodologies that came into play with 2 nanometer, 3 nanometer, like BSPDN, right? Backside power delivery network. What that means is that, you may be able to pack millions of those gates together, but what will constrain you is signal routing. And what constrains signal routing is power routing. So they came up with this scheme of, getting power from the other side. And what that did was that allowed more space for signal routing, and hence we could pack all these millions of, gates together. And that made the 2 nanometer, 3 nanometer chips happen. And as you compact, all these transistors closely together, it also leaves a lot of space for memories. And that's exactly what AI/ML applications need, right? They need a lot of memory on chip. So, with GAA, technology, they are controlling a leakage that, helps the edge kind of products with more logic on one single chip, more memory on one single chip. BSPDN, they are able to, obviously, and BSPDN, what it does is that it guarantees a very stable voltage supply at the transistor level. And so then you can really operate at the frequency that you want to operate at, right? So that gave rise to high frequency chips, which is again the need for all these advanced applications, AI/ML, or high performance computing. And so together, if you look at it, the shrinking of nodes, controlling of leakage, compacting more millions of gates together, more space for memories. So all this, so it's a chicken and egg, but application sort of drove the need to go submicron, but submicron is making it possible to make those chips, either is edge or ML kind of more bigger chips.
Thank you. It was a very interesting kind of description. In fact, we know that the cities are growing, and the cities are growing. As the cities grow, the multi-storied buildings, they start increasing. And in fact, we are now in the domain of towers, not just 2-storied, 4-storied, 5-storied buildings, but towers with more than maybe 25, 30, 40 floors. And such kind of scenario is being looked at when we talk about smaller nodes. Three-dimensional integration is the trend forward. But say supporting this three-dimensional integration, we need different kinds of technologies also. It is not very easy to go for the third dimension, increase in the building height. So it is here essentially we need to really go for very strategic planning. I'll ask a question to Bhairav Shah. What lessons has the industry learned from recent chip shortages, and how will they shape future strategies?
Thank you, sir. Thank you for the question. Hello, everybody. So to answer to what sir asked me, that how and what lessons the industry has learned from the recent chip shortages and how the future is going to be shaped because of this. So answering this, the first and foremost thing is one particular word that is called as supply chain. It's new for students, so I would just like to stress upon that a little bit. So supply chain is a concept which is often used in industry, where we talk about supplies of different materials, different resources to the industry. See, no industry can work as a single unit. It is dependent on multiple units, and this forms an ecosystem just like a food chain where different living beings are dependent on each other. If one of the living beings starts imbalancing the cycle, the entire system gets disturbed. You may take any company, any largest of largest company, it is dependent for its resources. Okay, say let's consider TSMC, which is world's largest semiconductor manufacturing company. It requires silicon, it requires gases, it requires water, it requires machinery. So for all these resources, they are dependent on other companies, which are again specializing into their own areas. Now, one thing that must be noted here is semiconductor being world's most cutting edge technology. All the suppliers in this chain, they are not built in a day or a week or a month. They are all experts in their areas, which have built their organizations into their specialities over years of research. So that is where the biggest lesson comes in, that is that we have to focus as students, as industry, on certain areas, clearly starting with the customer, as sir rightly said. And India, since being a consumer country, India since being the biggest, largest consumer, we have to be on the edge, right? Producing semiconductors closest to the consumer. Probably that is going to be the next thing. And it's really exciting to see the way our government has, our academicians are taking initiative to fulfill this situation. And apart from this, there is one more situation that is coming in is, since 2020, probably we realized that if the chip supply chain breaks up, there will be different impact on different economies, different countries, but we must notice that semiconductor has been driving world's research for more than 50 years, which was probably not visible directly. I mean, you can talk of man on moon, or you can talk of any latest cutting edge defense technology. Everything is driven by the semiconductor research. So my point being, the biggest lesson that is being learned here is that semiconductor technology has to be decentralized. And since it was concentrated in specific geographies, one of the biggest lessons that is learned by the world is it has to get decentralized. So countries like India, which is having such a large talent pool, has the biggest opportunity to grab these opportunities. So we must gear up towards these opportunities, starting with maybe ATMPs and eventually with fabs. So that's from my side.
That was a very nice and strategic answer. We have covered a lot of ground now through the discussion. So we probably have some idea about like what is the present status of the semiconductor manufacturing in the country. So my question to Dr. Basant Saini, who is a kind of visionary leader because he leads a R&D segment of a company. So it's basically what are the innovations that are expected in semiconductor materials beyond, say, silicon or gallium nitride or silicon carbide?
Thank you, sir, for the question. So I would like to answer this question in two parts. One is your question on the material side and the innovations in beyond silicon and gallium nitride. And before that, I want to talk a little bit about the advancements from the manufacturing point of view, sir. So how many of us are semiconductor engineers here, like who are enrolled in the batch? Okay. How many of us are mechanical engineers here? Okay, good. And people from the chemical engineering background? Good. So on the advancement front, okay, for the mechanical engineers, are you aware about a process called stamping? Do you know anything about stamping? Have you studied that so far? Maybe not, okay. So it is a very simple process, right? So what happens in that, you have a metal sheet and you cut it with a high force in a certain pattern, and that is used in our cutting edge technologies in our chip manufacturing. So it is a very simple mechanical process where a big heavy machine is coming from top, a metal sheet is beneath it, there is a mask, and it cuts it into a simple pattern. And it gives us something called lead frame. And that lead frame is used in chip manufacturing where the die sits, okay? Now, why am I telling you this? Because this simple thing, this simple process, still we are dependent on other countries or the ecosystem that is not in India. Now, can we do it here? Yes, we can do it. We have a very resilient copper manufacturing industry in India who has been doing, good business and been pioneering the growth of Indian economy. Can we translate it into semiconductor industry? Definitely we can. How can we do that? For that, we need to include our youngsters to make them aware about these processes, make these processes part of the curriculum, be it a mechanical engineer, be it a chemical engineer, or be it an electronics, or for that matter, a semiconductor engineer. And as Paul sir has mentioned in the morning, a civil engineer should know how a clean room is built, right, for us to have the talent pool. So I am digressing from the topic because I'm the last one, so I have heard a lot of questions, so I'm trying to put in my thoughts. Now coming back to the advancements in the technology. So what has happened is that earlier we were going planar. So when I say planar, what was happening, we have these integrated circuits, right? So what we do, we put them on PCB board and make them communicate with each other to do certain tasks for us, right? For example, people were giving example of a mobile phone. So in a mobile phone, you have these chips. There is a board. If you must have seen inside of your mobile phone, the chips are talking to each other and giving you a performance. They're sensing data, they're processing data, and then they're giving you some output. From there, people thought, how do we go forward? And Moore's law is a constraint there. So what they thought is, let us bring two chips, rather than going planar, let us bring them on top of each other. So rather than moving in two-dimensional, let us move in three-dimension. Use the third dimension. So how they started with it, so what they did was that the dies on the silicon dies, what they did was they started stacking dies. Now on the lead frame there is a base die, and top of that they have put another die, and they were connecting it to the lead frame and the substrates. It was still a physical connection that they were doing. And there were a lot of issues like transmission losses, signal was getting delayed and impedance was high. So what happened next in that journey? People thought of, instead of doing this, let us integrate it at the device level itself, at the die level itself. So what has happened then, instead of creating physical connections, meaning connecting one die to another using a wire, what they started doing was, in the fabrication process itself, they started connecting chips or dies to each other, and they started stacking them. So that was die integration. So rather than using wires to connect two dies vertically, they put dies on top of each other, and there is something called interposers. I want you all to go and look about it. And through silicon vias. So what they did was, in the silicon, they etched it, they filled it with metal, and then they connected dies vertically. Now people thought, oh, okay, this is, so all your high bandwidth memories like we are using today, they are based on this technology. You integrate all the data center chips, all the GPUs, they use these chips, right? So here you are integrated, the dies are integrated vertically. You have almost 30 dies on top of each other, and you are getting, in a small area, you are getting a larger memory. Now, what has happened beyond that? That is something that should that should resonate with the freshers who are there today, and that is still work in progress. That is the silicon integration, meaning you are integrating the dies at the silicon level itself. So what is happening there is that there is one kind of wafer, and then there is another kind of wafer, and you are bringing these two wafers and you are attaching them with each other. Rather than doing connections through traces or physical wires or using interposers, these two dies are very close to each other, and they are connected directly with each other. So you have reduced the metal length that was connecting them, and you are reducing the losses. So I'm not trying to go too much into the depth, but what I want you people to go and look about is silicon integration. So how we are connecting two wafers with each other, and that things like hybrid bonding, copper to copper bonding, that is basically enabling that. So meaning we started from using planar chips, communicating with each other through wires, then we started stacking them still using physical wires, then integrating them using vias, and then now we are at the level where we are integrating at the silicon itself. Now this involves not only semiconductors, okay? Here, people with expertise in mechanical engineering, people with expertise in chemical engineering and material science are required. So these, semiconductors is nothing about semiconductors. Somebody taught this to us, and they said, if you want to learn semiconductors, go learn your chemistry, go learn your mechanical engineering, go learn your thermal engineering, and then finally go learn your material science. So it is an amalgamation of all these engineering aspects, and then you finally see a product coming up that you call, the background of it is semiconductors. So that is the technology development that is happening currently, and we all should be part of it, and that is where industry is trying to go. On the material front, sir, like your question was pointed to, we all know that silicon had been there, is there, and will be there. Beyond silicon, what all avenues have opened, so they are very product centric. For example, if I were to make an LED today, I will use gallium nitride for sure, and that is a standard material to go. If I want to use a display, I want to use a material for display, people have done good progress. They have moved beyond gallium arsenide to gallium nitride to now we are using organic LEDs, right? So we are making good progress. We are moving beyond the traditional materials because the polymers are giving us very good performance. So in that direction, so it is very product centric. People are not focusing more on the material. People are focusing more on the product and which technology can give us best results there. people have explored a lot using polymers for solar cells. And at one point in time, we were getting so many grants from ministry and government all across the world on exploring polymers for solar cell applications, for photovoltaic applications. But where it eventually went into OLEDs. So people started to explore it for solar cells, but then they found that it has a better use in organic LEDs, and displays came into the picture. Same stories with graphene, right? So we have heard, we all did research, we were listening that graphene is the next big material. But it could not boom out like that, but it found its applications in cutting edge chips today. So you would be surprised to know it is even being explored to be used as a thermal insulating material in the cutting edge chips. So people see materials on the basis of the product and the application, sir. And the material that we are choosing is very much driven by the customer's requirement and our product development.
Yeah, that was a very well covered kind of answer, though he said that it is a slight deviation from the original question, but actually he touched upon the topics which are more relevant, because those are essentially related to the interconnects between the chips and even going for the multi-chip modules and essentially the kind of integration that happens in the third dimension. This was round one of the discussion, and in fact we have covered a lot of things during this. There were actually, as per the plan, there were 3 rounds, but I'll now squeeze, looking at the time, I'll squeeze them into 2 rounds. So maybe this time now the order will be different. So we'll start with Dr. Vivek Kumar. The question to you is, what are the biggest challenges in semiconductor fabrication, and how do you look at whether academia can align with those standards?
Okay, thank you, sir. So, about the challenges in VLSI fabrication or semiconductor fabrication, the backbone is again the same, several panelists focused on the Murray law. Murray, he was the founder of Intel, co-founder of the Intel with the Robert Noyce, Gordon Murray. He given, this was not a law, this was just a prediction. After that it became the economical basis of Intel. They followed that prediction given by their founder, and till now they are trying to follow that one. Rule was simple. In earlier, first he told that in 24 months size will be half, number of transistors will be double inside the same size of chip. After that he reduced that duration, that was 18 months. So earlier when in Intel 4004, that was the first processor fabricated in 1970, in that time size of the transistor was in micrometer. And nowadays, if you will check in your mobile phone, you will find there is a FinFET technology, 14 nanometer. Currently, industry is exploring about the stack nanosheet field effect transistor, that's a gate-all-around transistor, CFET. So these transistors have the channel length around 5 to 10 nanometers. 5 to 10 nanometers, if their channel length, then their oxide thickness is around 1 nanometer. 1 nanometer means, if you will compare it with the atoms, this is like a stack of the few atoms. So fabrication of few atoms, like thickness in 1 nanometer kind of device, like oxide thickness, silicon dioxide. So it is very tough in the fabrication point of view, because fabrication is not so, it's not visible. Whatever you are doing, that is on the basis of your GDK file and your optimized process. So due to this minimum size, this size is creating a problem for the fabrication, because a 1 nanometer thickness oxide fabrication, it's very difficult. Another, if you will see, for the transistor at the few nanometer of channel length, so there is a problem. That is the short channel effect. Short channel means gate have less control on the channel. So to reduce that, industry shifted towards the gate-all-around device. That first one was the FinFET. 2014, I think Intel shifted in that technology. After that, now they are trying to shift in maybe 26. They will shift to nanoseed. So this gate-all-around device has the 3D structure. Earlier MOSFET has the planar structure. Fabrication of 3D structure is very complex compared to the planar structure. So one challenge of that fabrication is that the size. Second, if you will see, that one is the variability. Variability means if you are fabricating a 100 nanometer oxide or maybe 20 nanometer oxide, if one atom will be misplaced, there is no problem. But if you are placing 10 atoms and one atom is missing, then there is a biggest problem, because it's going to completely affect your threshold voltage. Threshold voltage is will affect your circuit performance, gain, everything. So variability is a very big challenge. Another, reliability. If your device thickness, like oxide thickness, is like in nanometers, few nanometers, then there will be mechanical tunneling, quantum mechanical tunneling, because thickness is very less. High energy electron will break it. So leakage will be higher in that. So these were the problem with the existing CMOS silicon technology. Another problem with the fabrication, if you will see nowadays, few new materials come into existing, like ferro, 2D. They have a little bit some potential application in a specific area. So integration of these atoms with the silicon is also a biggest problem, in my opinion. Okay, thank you.
My next question is to Mr. Kedar Patankar. The question is slightly different than the technology aspects. It is related to whether the Semiconductor India mission has been able to attract investments, and is it effective?
Okay, thank you, sir. I just keep reading news about it, right, like all of us. So I know that there is a manufacturing plant being opened in Gujarat, or they are opening it up this year, and one is in Odisha, and I read that government is putting allocating so many funds and all that. So I'm yet to see the results, and I'm positive about it, because obviously we all understand that we are late to the party by at least 20 years, but it's better late than never, right? So it's good that government is putting in focus and funds, and academia is now talking about it. But to create an ecosystem, I think somebody was saying, that's a big challenge, right? How do you create ecosystem? We're talking about packaging. At least the companies that I worked with so far, I see so many chip designing engineers, but the groups that do package design, people are fewer. Or, I know that, some companies are there in India which can do package design, but package manufacturing obviously was happening outside India. And now we are doing, we are planning to do it within India. I'll be curious to see the business case of it. So, once they start manufacturing the packages in India, who the customers are going to be, because if you look at the product companies who are going to be the customers, product companies will have to make decisions between them and the established players who are outside India, or whatever. And if you look at the landscape, most of the product companies are MNCs. Now, so that's one angle, right? That's the business angle. Obviously, if you think about defense or security, then having that ability within India is key from that angle. But if you want to build workforce, now I've been on board of studies of at least 3 colleges in Pune, and been interacting with students and faculties, and only now we are sort of really paying attention to creating programs in semiconductor and VLSI. Until now it was generic ENTC degree, which didn't really help us, right? So to create a knowledgeable workforce, I think, from packaging point of view, for example, it will require academia to put in significant effort in creating those kind of courses which are industry industry ready. But even within industry, I think even experienced people who are working in the chip domain, for example, they don't really quite understand the package and chip interaction, and why package design is so important. A chip has to work within a package, and that package has to work on a PCB, right? A chip cannot be just tested on its own. So from package design point of view, package design and chip design almost has to be co-designed. They have to be co-simulated. There are aspects like signal integrity, power integrity. There are aspects that interactions between package and die and PCB and package, like resonance. So all these aspects come into play when you are putting a chip in the package. So to build those kind of expertise, how do you design a package, how do you simulate the package along with the die, and then how do you put that in the PCB and test it out before a product can work in the real world? Those expertise, I think, we need to build, and that effort has to start from academia, and then obviously, like we said, government is putting in money, but I will be curious to see the results of it. So I'll be positive, but results yet to be seen.
Yeah, it is covering interesting component, and you mentioned about packaging. In fact, India Semiconductor Commission also has focused on ATMP very much. In fact, there is a major component that is coming in. So my next question is to Mr. Bhairav Shah. What role should industry play in shaping the academic programs for getting job-ready ATMP engineers?
Thank you for the question. This is a very nice question. And every institute that I have been visiting, most of the faculties I have been discussing this, that in what way the curriculum needs to be designed and how the academia can get ready for the industry. So absolutely, I mean, the first starting point here is going to be the customer or the consumer of the chips. And then starting with the ATMP technologies. Now ATMP in itself is a very wide domain, because there are different conventional technologies, as well as there are different advanced packaging technologies, may it be flip chip or may it be the conventional packaging. But for academicians, I think we should focus more on the basics, and it starts with the language of engineers. So what is the language of engineers, my dear friends? Can you please? So I think it starts with maths and engineering drawing. So the very first and foremost thing, in my opinion, is the interpretation of engineering drawings is a skill that will be very, very important for ATMP engineers to start with. And going further, basic processes, basic mechanical processes, and manufacturing processes have to be mastered, because if you take an example of car assembly, now since we are sitting in the hub of automobile hub, since we have a lot of car assembly plants, a car is of order of magnitude of few meters, right? Which is assembled. You must have seen it is assembled completely by a set of robots, a line of robots, which is having a hell lot of SPMs, which are working in coordination, which are fully automated. Similar is the assembly of chips, but you must note that the order of magnitude comes down to few millimeters. I'm talking about the package size. The car size is of order of few meters. The package size is of order of magnitude of few millimeters. Now, when you are assembling a car in a fully automated setup, it requires a precision of all components within range of tolerance of 0.1 millimeters, that is 100 microns, for assembling a car, which is as big as of 1 meter, you can say, order of magnitude of 1 meter, so few meters. But when we are going to package a chip where there is going to be absolutely no human intervention, where it is going to be assembled with the help of automated machines, which is of order of magnitude of few millimeter, the tolerances or the precision that we need to achieve there is going to be of order of magnitude of submicron. So achieving the repeatability, the precision of submicron precision for ATMP is also quite challenging. I mean, since ATMP is the most lower hanging fruit, submicron accuracy has to be achieved, achieving it every time. See, the rate at which the chips are assembled is not a slow rate. You're not going to be assembling 100 chips, 200 chips a day. Thousands of chips are to be assembled in a day with submicron repeatability to me, that's a challenge. To achieve that, we are going to need very good automation skills, robotic skills, machine maintenance skills to maintain these machines continuously operable. We don't want breakdown times. And I think this is the real opportunity for students who are pursuing their career in ATMP. So the academics has to closely collaborate with the ATMP companies to understand their requirements like operating the machines, maintaining the machines, then Industry 4.0, that is predictive maintenance is what I'm trying to stress upon. We could have projects from institutes which are focusing on maintaining these machines and how advanced technologies like AI and ML can be deployed for increasing the production, optimizing these machines, and etc. So that's from my side, that from conventional packaging to advanced 3D packaging, how the academia has to gear up with fundamentals of engineering, starting with mathematics and engineering drawing.
Yeah, it's very good strategically planned answer. The thing is that many a times we talk about industry-academia gap, and the industries, it is considered that industries are always leaders in technology. But it is the other way around situation many times, because academia is performing a lot of research activities, and these research activities, if they are to be brought into practice, there is sufficient amount of intervention needed from the industry side. So I think we'll take this forward with Mr. Yevle, Ranjit Yevle. What are the new skills required for implementing the strategies of future ICs?
I don't think so you need any new skills, right? Like the only message, probably in the interest of time, what I want to say is, and from our experience and most of the panel members will agree, so you guys have to start putting lot of hours into the labs and more than the classroom hours. So that's probably, and that's where, to just add to the previous question of how industry can support. So that's where you start working on the problems what industry has. And as Sir rightly said, academics there is a perception that academics is following industry, but it should be the other way around, where academics has to do a lot of research, have to interact with the industry on daily basis, I will say on the hourly basis, see what the industry needs, what are their problems, because the industry is already occupied, I don't know, maybe 150%, 200%. So they don't have bandwidth and energy to work on all their wish lists. So probably if academics can go talk to them, sit on the same table, take the problem statements, come back and start working on that, I think that's first. I don't know if we can define it as a skill, but that's probably what we can start with. And then I think industry is always ready, because industry needs solutions and industry wants the resource pool to be built for next 5 years, 10 years. So that's most of the guys are doing. So if we can just go and see what are the problem statement industry is facing, and probably try to solve it at our level, and then have this kind of discussions where you go back to the table, see what the solutions we have, what are the current limitations, work on that, come back, and then just keep on improving this loop. So I think if we start there, I think whatever industry, India Semiconductor Mission and all those fancy stuff what we have been talking about should not be a dream anymore. It could be a reality in next 5 to 10 years. Yep. Thanks.
Thank you. It's a very kind of straightforward answer, one should say, and that probably could be an eye-opener for the academicians. We'll look at the other aspect of it. I'll ask this next question to Dr. Basant Saini. What are the key opportunities that you foresee? Because we see that anything which is related to the packaging, that involves the design not in terms of only the placement and the routing, or essentially the optimization in terms of maybe the heat management or maybe the stress management and material management and so on. So what are the opportunities and challenges in building global competitiveness? Because many a times we just copy the designs which are available elsewhere and we get satisfied, oh, we are very close to them. But actually, can we be the leaders?
Sir, I'll start by saying this thing. As an engineer, I don't mind copying, and I should not mind. I mean, this is something that I'm saying in front of the young minds. I don't want you to think that this is a bad thing, and I can give you one example. To start everything from scratch, that is Indian mentality. I mean, we want to excel in something. We don't want to take up somebody else's work, and we want to build from zero. I mean, the industry, the pace at which it is moving is like leaps and bounds. And if I start from zero, I don't know how competitive I'll be in the next 10 years. So I'm saying it in the open forum. Let us not shy away from copying as an industry also, and that is what engineers do. When I say copying, it doesn't mean that I'm copying somebody else's patent, somebody else's IP. What I'm trying to say is, I should learn from what others are doing and modulate it into a way that fits our ecosystem. So there is an Indian way of doing things. We should learn and adopt. So that is the first thing that we should do. And then second thing is, when we get comfortable in that, then naturally we start innovating also, sir. So innovation doesn't come from an investment. It doesn't come from, some people say it comes from the need. That is fine. But mostly it comes from the position when you are comfortable, when you are meeting your requirements. When I'm meeting my chip requirements, I'll be in a stage where I'll get comfortable and start thinking what to do else. What else should I do? How should I innovate? So I think we should not, no disrespect. I am in the R&D team. I always try to see what else we can do in the packaging domain. But what else can I learn from others who are doing it already? Be it the ecosystem that is in Southeast Asia, be it the ecosystem that is in Europe, be it the ecosystem that is already there in US. So what can I learn from them, and then how can I implement it in India? That is the first thing. But that doesn't mean I should let go of my innovation part. Always visionary leaders, visionary companies, they invest and they always have this vision of doing their own, building their own IP. Side by side, we keep on doing that, but customer requires solutions. And if, trust me, if I look at the market that is deviating from, like when we are looking globally, China +1 and all that, they are not looking at me because they want to do some cutting edge technology today or they want an innovative solution. They just want to see what can I provide to them, what is already been there in China or Southeast Asia. If I am able to give them that, they are happy. And I'm not talking about some random companies. These are the likes of, big names, right, all over the world, who have been established players in the semiconductor industry, be it your automotive sector, be it your high performance computing, be it your AI. They all are looking at India just to provide a solution that is already existing. How we can do that here, how we can do it in Indian way, like we have done it in IT sector, like we have done it in automotive sector. Can we replicate that in semiconductors also? That is their way of looking at us. And that doesn't, let us focus on, that should not stop us focusing on research. Definitely it should. But let us get comfortable first in doing what others are doing. And let us adapt that at a scale where we can say confidently, look, 30% of our GDP is coming from semiconductors, or 40% of our GDP is coming from semiconductors, like it has been for countries like Malaysia, Singapore, China. Then I think we should simultaneously look ahead for innovations and development.
Yeah, that's a very well said thing. Actually, it is not a very bad thing to start with copying. There is a new terminology that people are say introducing for this concept. It is called immovation. It is imitation plus innovation together. So with this innovation concept in mind, we look at like what is the kind of innovation that one can look at. It is incremental innovation, or it could be radical innovation, or it could be completely new idea and disruptive kind of technology concept. Now we come to the end of this panel discussion. Finally, I'll ask a question to Dr. Ashwini Agarwal. What is the interdisciplinary knowledge that we can look at? Because India has been known for marrying various kinds of interdisciplinary concepts and bringing out innovative products. So how does the interdisciplinary knowledge play a role in building the future workforce? Because that is what we are really looking at. We say that India has the biggest advantage in terms of democratic dividend, and this democratic division is essentially that we are basically specializing in. So if you can give your inputs on this, thank you.
Okay, Arvindji and rest of team, I think convergence is the new Moore's law, a new dimension of the Moore's law. Yes, you need specialization, let there be no debate on it. But there is always such a thing like over-specialization. And, the entire design of our curriculum, the entire design of our job roles, it has to go beyond over-specialization into a systems thinking, systems thought process. Today, the final product that will come out will not be the result of just one single technology or one single discipline. It's going to be a result of convergence of a lot of different technologies, and to that extent the talent that has to evolve has to go beyond and be able to deliver that. So there's no debate on it. You will need interdisciplinary knowledge to shape the products of the future.
I think we have come to the finalization or conclusion of this more than 1 hour long panel discussion. One quick question for everyone. You can give your opinion in one or two sentences. This is basically, since we are in the midst of the engineering academics, and what probably are your expectations for the academicians, especially the teachers and students, as well as the managers of these academic institutes? So in a couple of sentences, you can just give your opinion. Shall I start?
Okay, I think, Dr. Priya, you need to build the concepts and you need to go to capabilities. Move the children from a handbook to hands-on. That's a quick message.
Oh, I think when you are designing curriculum, what is important is that, why are you teaching a certain course? I think that's what's missing. Because every time we design a curriculum for a semester, why a certain course is being taught and how that course helps in the big picture. So you got to show the students big picture and then, make sense of each of the courses that you're teaching. And then I think the sequence of the courses is also important, because I see a lot of random courses being placed in semesters and they don't sort of all contribute to the big picture. So I think students need to understand the context of why a certain course is being taught and in which order. And also to be able to do that, what is most important is training the faculties. And I think once faculties are trained with real industry level designs and test cases, and it should be a comprehensive training, not like, a couple of days seminar, then I think they themselves will understand the big level picture, and then they'll be able to, I think, impart that knowledge to the students and give the context.
Ajay, like your university launched the semiconductor technology course. So that curriculum-wise, you definitely they will teach device physics, circuit, system, coding. So in my opinion, for the hands-on, a student should have at least 1 year project. That project should be based on FPGA. So at least they can implement either, there are mainly three types of VLSI design. One is the ASIC, custom, or FPGA based. So at least FPGA type design, or they can tape out is simple chip. It's not like that you have to design the processor in their final project. They can maybe design SRAM. They can go from the basic transistor to the GDS file generation, and then they can submit. There are several sites are there. eFabless, they have the open PDK, like Sky PDK. You can submit your design there, and they will get it fabricated for you. There is a minimal charge for the students are there. So that can help to maybe a little bit reduce the gap between the academia and industry, because they are looking trained student who can contribute. And only that is possible by the hands-on. Hands-on is the project, maybe FPGA or maybe some Verilog to chip design, maybe transistor to chip design. Okay, that will also only the possible way to help the industry. Okay, thank you.
Okay, so first of all, I would like to congratulate D.Y. Patil International University, who has given their students this platform where you have a hands-on lab where whatever you are doing in theory, you can go and practice it. So trust me, when I was doing my undergrad and even my masters, I used to always imagine what would a lithography tool look like, because I would study that from SMG and all that, right? What would oxidation look like, process look like, or metallization? We used to cram those and write our exams. That's it. Then came the virtual labs, and now you have a physical lab. So make the most of it. Coming to the question, in the industry, what do I see when I interview an undergrad, right? So you are graduating, and I don't see, I don't want you to have to know everything. But if you have in your 6 months or 1 year of project, that gives me a talking point to you. Like you have done some project, maybe even if you have fabricated a MOSFET in your lab, that will give me enough confidence to talk to you about your skill set. Or even if not a MOSFET, if you have just done oxidation process, I would gauge your knowledge on the basis of that as an interviewer. So first and foremost is your basics, then practice that in the facility that you have. And a very well raised point, in fact, I also wanted to say that each one of you in a group or individually, do the tape out, okay? Select an application. You have open source PDKs available. You have tools available in your lab. Start from the second year onwards, and by the time you graduate, you will at least have a GDS file ready with you that you can push your faculty to get a physical wafer fabbed out or physical chip fabbed out from the foundry. If not, still you would have the tape out done by your hands, and that will give a lot of confidence to the interviewer. Okay, this person has done design, digital design, analog design, he knows or she knows. So that is another aspect of it. And if you reach to a tape out, you get your wafer or chip fabbed out, come to us, we will do the package design for you, or you come to us, we will train you in package design, and you do the packaging yourself. So that is also where I see that you should do. Or even if you do either one of them, either do chip design, involve in a tape out, do master a fabrication process, or practice all the processes that are involved in a MOSFET fabrication, that is good enough. And improve upon your basics. You will be surprised when we interview freshers, sometimes they are not even able to talk about Ohm's law, right? I'm not demeaning it happened to me also, because we go so much depth into band gaps, semiconductors and all that, we forget about the basics of the physics. So as sir has also pointed out, keep on following the language of an engineer, that is your physics, chemistry, maths, get your basics correct, and along with that build upon the expertise with the tool sets or the facilities that you have. Thank you.
For me, I think there is nothing like expecting anything out of anybody, right? This is like a very formal, professional give and take relationship between academics and industry. So I think if you are very clear about, because this is about, when we are talking about ecosystem, everybody has to play a role. If you understand your role, even if you are a student, faculty, or a management or industry, if you understand your role very clearly, and if you can work on it minute by minute, I think this breach will be done by itself. We don't have to, and probably for each role, I am sure we can have a debate like this, and then talk about what that role is and how we can make this ecosystem a more sustainable system. Yep. Thanks.
I personally feel that hands-on, of course, is extremely important compared to the memory-based system that we have been conventionally following. As sir rightly said, that we used to memorize the processes and write down our answers, but you are lucky that you have a lab where you can have hands-on onto all these semiconductor processes. So in my suggestion, having hands-on and mastering the semiconductor fabrication processes, or even mastering one process in itself, will be a big activity. But there is one caution that I would like to raise, or a disclaimer, that is, we need to have a collaborative hands-on activity, that is where we have industry, where we have academia and the students all together, specifically working on specific processes, trying to gain some results out of it. That is result driven, firstly. Secondly, what I feel is, see, the chalta hai attitude nahi chalta here, specifically in semiconductors, because we are talking of submicron and maybe even beyond that. I mean, submicron as an entry point at ATMP. If you go to fabrication, there again the dimensions are changing. Very soon we will be going subatomic. So the point that I'm trying to raise here is, while we are talking of hands-on, we must be extremely serious about it and not just doing it as a fun activity. Or rather, there has to be a disciplined, systematic engineering approach towards the labs that we are trying to work on, and trying to build the engineering discipline in the way we work in our labs should be evaluated or stressed upon more than how we memorize things. I'm repeating my statement. How we perform our engineering systematic labs than how we memorize is more important. That's what I have experienced while working with all cutting-edge global engineers. The way they carry out their experiments, the way they systematically plan tests, these are the things that we must try and learn in our labs. And that is where I think the industry and the academic collaboration is going to be extremely important for such critical subjects like semiconductor technology. Thank you. That's from my side.
Yeah, thank you, one and all. All the panelists, they have actually shown to the audience that why they are here, because that's their kind of specialty that they have demonstrated very well. Thank you all. Basically, our Prime Minister at one point of time suggested that there is vocal for local. Probably we need to really look at the scenario, and today's panel discussion that essentially went from global to local. Like we started with open challenges, open scenarios, and now finally we have narrowed down to what essentially will be done by our academicians, our students, teachers, so that they become globally competitive. So the loop is essentially growing in that manner. We really need to understand that every time when we talk about semiconductor technology, we need not really go into nanometer or sub-nanometer scales. We have 180 nanometers also. What is wrong with it? With 180 nanometers, we get the chips, and these chips, they are functional. Even today's applications, many of them, they are working with 180 nanometers or even larger. Yes. So that is where every time we need not talk about, maybe some percentage of us can be really focus and we get into the domains in the cutting edge kind of technologies, but the other ones we can essentially focus and try to make successful chips which are working in the field. And for this purpose, I think the kind of amount of skill that is required will be personal level skills. It is not really very high-end kind of skills required, because one need to understand like what is oxidation. So we say that oxidation is putting the wafer in the furnace and having the oxygen or oxidizing ambience and then maintaining the temperature and so on. So all this is done, but what is the control over the thickness of the oxide? The control over the thickness of oxide cannot be mastered in just one go. We have lots of skills to be learned before we get exact control. Say for example, the rapid oxidation region in the silicon oxidation, that is the region where essentially it is of the order of few angstroms of oxide, and this oxidation region is very much difficult to control. Now naturally with lot of practice one can control it, but every application doesn't need this. Every application doesn't require a MOSFET which is very small in dimensions. We require lot of large scale devices. Every application need not be FinFET. Every application need not have, say, what Dr. Vikram Kumar said, turn around kind of gate. Those technologies, they are there. They are the state-of-the-art technologies and they are taking forward. But at the same time, we should have our mindset for providing the solution to a given problem. So we have some problem, and with that problem, what is the best solution that we can offer? That we should be able to try it out, and with facilities what we do have here. Say for example, I'll just share with you one of the things that we really worked on. That essentially was related to developing photolithography technology. 30 years back, 35 years back, we essentially started working with it. Now with the photolithography, that time was very much in infancy for us. Probably elsewhere in the world, the photolithography essentially existed and it was working at submicron level at that time. But we got satisfied by producing consistently 50 micron. So 50 micron was our line definition, and we consistently produced it. It is not by accident on one of the days it comes 50 microns, the other day it is 75 micron, nothing like that. Consistently we asked for 50 and we produced it. So we are very proud of that particular achievement. Now there are opportunities where we can see that we need not really look at getting into the processor fabrication, because we are basically in the domain of Internet of Things, and IoTs, they work on very small processors. Processing power, compute power required on the IoT nodes is very small. So can we focus on IoT kind of technology chips, where there is a standalone node, which basically one says that it is edge computing kind of node, and that edge computing kind of node has got something like the sensor and sensor interfaces. In fact, integrating sensors into the chip, that also is a very big achievement, because we see that there is another branch which is basically very much progressing. That branch is, we didn't talk about that here, but that branch is basically related to MEMS. MEMS technology doesn't talk about submicron or subnanometer kind of scales. MEMS technology is essentially custom CMOS technology only, but this technology essentially creates mechanical devices which are small in size, not
physically machined, but chemically machined. So actually we should essentially target on such things and develop, because we see that many of the cars, people talked about car application, automotive application, many of the cars make use of what is called as the airbag. And the airbag release technology is based on MEMS. We do not have MEMS fabrication facility in the country. There is no MEMS device fabricated in the country which is deployed in the cars, automotives. Can we target on that? And then we produce something which is supplied to the industry. Automotive industry is the big industry. So we have to identify such niche areas wherein it is possible for us to get them delivered within short time. And we target for the other, say, advancements in the years to come. So I think it was a very nice discussion that we had today. And with this discussion, we probably can look forward for progressing in the semiconductor technology domain. And I wish all the best for the organizers. Thank you.
Thank you to our esteemed panel for this enriching discussion. We would now like to engage with the audience. If anyone has a question, kindly raise your hand and we will come to you.
Good afternoon. My name is Tanishka. I am from Semicon department first year. My question is, what startup opportunities are there in semiconductor domain in India?
Hi. I will tell you what I know. I think, you know, so if you look at the Indian landscape, right, over the last 2 decades, we have been very services-based country. So MNCs come here and they want to do some, design services. And so a lot of engineering workforce has been doing design services. So basically that means that you are doing VLSI design, and I'm speaking from VLSI design part of it because that's what my background is. But so you are doing VLSI design for a product company which is not Indian, right? So an MNC is going to come in and give a contract to some other services. So if you see in Bangalore, in Pune, in some of the areas, there are like number of services companies who are doing chip designing for a product company. So in India, if you have to build a startup, that's where, because to build a startup you need people. And you need right talent, right? Apart from the money part, that's a different thing. But pure talent, now where do you get that talent from? Because the talent around you will come from the same background that I described, right? So unfortunately what has happened is that on the product side, a lot of these product-based decisions, where companies thinking about a product and they're coming up with spec and functional and architecture level decisions, they have been happening outside India. And so our workforce is so used to just following a design, say after RTL, and taking it through GDS2. We have very limited people who can really think from product spec point of view. So what we are dependent on are people who have worked outside India, who can come here, who are ready to come here and really put in their expertise to start something like that. And then they will be dependent upon the workforce to really get that product or startup successful. One area is, so a lot of startups that I see, they are doing design services. So, and their goal is to basically get acquired eventually, right? So they will do design services and they get acquired by some other bigger, larger design services company. But if you want to do product, one area is EDA. Right, so EDA tools like Synopsys, Cadence, those EDA tools. Now you have to come up with an idea, you need to be experienced enough. And again, that goes back to my, if you have the right founders with right talent and background, they'll be able to pinpoint to an area that the big companies have missed and create something in there. And then they will require people, or graduate students who have VLSI plus programming background. So EDA is one thing. Services is the other thing. If you want to come up with a SoC or a chip level product, that again is dependent on the people who have enough know-how of the industry, various industries, where they are able to say, oh, well, there may be a need for and then how do you compete? Because every startup needs a business plan. And, I see a lot of talk about innovation and, ultimately innovation has to result into something which is out there in the market. Otherwise, innovation is a waste. So for any startup to have a right business plan, you need right people with right background who can identify those gaps in the market. And again, from Indian point of view, and those people need to have international experience because they need to have again mingled with architects and those kind of that kind of community to really pinpoint that need. So to start a startup is not easy, but again, like I said, for you guys, your services, EDA, and then if somebody starts SOC, then that's a great company to be in.
Thank you.
Please give a mic to ma'am.
Okay. Very good afternoon to all the esteemed panel members. I'm Dr. Preeti Rajput from Pimpri-Chinchwad College of Engineering and Research. It's a great pleasure basically that we see such a distinguished professional on one forum. So specifically I would like to acknowledge Dr. Vivek Kumar sir, whose guidance has been invaluable in my semiconductor research journey. So in line with that, her actually question, so if we wanted to start our startup, okay, sir, you have given the, the correct approach to start this startup. In align with that, the current feasibility, which I want to check, then what are the potential low-cost investment approaches to enter this particular space? And another thing is does the certifications really help to enter in this particularly industry-related programs? Thank you.
Thank you, ma'am, for your acknowledgement. Okay. However, your question is very big. In lengthwise also, even Mr. Kedar already explained a lot about the type of a startup. You can do a startup in the service, EDA tools. If you will, EDA tools is not like on a circuit design only for the cadence. If you will go for the device level, you need to design a MOSFET and you have to optimize it for that is called as a DTCO. So designing a MOSFET at the device level, designing a SRAM or some inverter at the circuit level, you have the cadence or synopsis tools. At the system level, you have the Verilog. So these tools I think cadence have the huge license fee. Government of India purchased, I think, in the bulk and distributed to, I think, several institutions under the C2S program. But these EDA tools are only math models plus coding. So as a Indian perspective, we have if we have dedication and we can work like IIT Madras few faculty, they already a startup to developing EDA tools for the device simulation. So maybe made in India concept. If everything is there, that's not our concern. The concern is that for us, if we are paying the huge amount of license fee to the synopsis, cadence, that is very a serious concern for us. So if we are a good programmer, we can make a team of a good device designer, have the good physics, and they can collaborate. Before you ask the funding, before the funding you need a talent, your dedication. So if you have Government of India has several initiatives. If you will see, they have several call for that. You can submit your idea. They will fund. Even TIH is there in I think IIT Bombay, IIT Madras. I think mostly IIT have the plan incubation of the startup. So first thing you have to identify the idea. You want to focus on which direction, EDA, or you want to work as an outsource for the Intel. So a small part of their work you can do. So for all things you need your training, and training only is the possible way, and first step for the funding is the second step. Okay, so and other things already Mr. Kedar explained. So thank you so much.
Thank you, sir.
Hello everyone. Myself, Dr. Anita Deshmukh. In line with this discussion, I would like to request you to focus on one point, is that Vivek sir, you mentioned about the FPGA design. And whenever I talk with any person related to the VLSI, everyone shows the picture that VLSI means FPGA design, that's all. Okay, this is in general. I'm not saying everyone, but in general. And no one talks about the analog and mixed signal design. So, can you please focus on the comparative opportunities for the analog and mixed signal design and digital design? Thank you.
Ma'am, really this is a good question. FPGA, why I told FPGA? If you will tell a second year student to design a complete ADC from using the MOSFET, there are several things are there. I am just telling about the SOC point, means a chip point of view. There are other things are there, packaging, like your management of the floor, physical design. There are several things are placement. But if you want a design a chip in a small volume, like if any bank needs some system, if any thief will come, then it will generate a alarm. That is very, very basic, toy problem. So for that, a specific bank, there has some specific scenario, if it's from the Pune or somewhere in the Gujarat. So they have their own conditions. So for that one chip designing, no one will go to the foundry. We are not going to design a bulk 1,000 numbers of chip. So, but if we are designing a processor for mobile phone, the same mobile phone will be sold by, I think, several companies. Like Qualcomm processor is common in all. Like if you purchase the Motorola phone, you will for a Samsung phone. So there is I already discussed, there are three types of design, basically classified design. One is that custom, another one is the ASIC, and third one is the FPGA. FPGA at the prototype level, that is the first step of the design. If I will tell any student, okay, you design a full adder, or that is very basic problem, full adder on the FPGA, that's very easy. He will write some very log code, he will write test bench, he will dump that code on the very low FPGA board, and now that board will behave like a chip. Again, if I will tell the same student to design a GDS2 file that will be used for the fabrication at the foundry, so that will be difficult for him. So I think if you will ask anyone, so for the initial learning purpose, even industry people will suggest that, okay, you should go on the basic problem of the FPGA. If you learn that one, then you can approach to the analog design. Analog design means like you can design amplifier, instrumentation amplifier. At the mixed level design, you can design some ADC, DAC, but these are very complex. If maybe fourth year student can take that type of problem in a 1 year, maybe MTech student can take, but you can't expect the same thing from the second year students. Coding means like if they know C, they can write the very low code also. I think patterns are almost same. So to save the time and like your cost, FPGA design is preferred at the prototype level. But if you will go at the higher volume level, then there is the analog, mix, or SOC design. Okay, maybe I am clear, right? Thank you. Ma'am, I will just add to that. So thanks for that question, because it's an important area. I think what you asked was a differentiation between digital design and analog design.
Excuse me, I asked about the opportunities.
Yes, I'll speak about that. So just to be clear, for students, the digital design can be done in FPGA or SOC. So, standard cell-based designs or FPGA. So, but coming to analog, in industry right now, there's a dearth of analog layout and analog design engineers, and most of the SOC products or projects that are coming to us have a big analog interface, and naturally so, because world is analog, and so every chip needs to read some analog signals inside the chip, convert into digital, and then process it. So to answer your question, absolutely, if academia can create programs to really in 4 years or in 2 years create really good quality analog design and analog engineers, that's what industry wants. And along with just analog layout and design, we need to also focus on integration of that, because that analog piece is going to go into a digital chip. So what happens is that the challenge becomes between the boundary of analog and digital, right? When the analog ultimately processes gets through ADC and goes to DSP. That's where the timing becomes important. Mixed signal verification methodology becomes important. So there are EDA tools to do that, but people who can do that are limited. So absolutely, very, very good question. Academia should really focus on good analog design layout and mixed signal verification coursework, because industry wants that.
Yes, sir. Even noise handling is also very critical.
Everything becomes critical, because you talk about SerDes, right? High-speed interfaces, anything that gets into the chip, and analog being such sensitive, and then obviously you have DSP after that. But you want to be very, very clear about the noise, the crosstalk, and the signal integrator and all that, right? And then, like I said, mixed signal verification, functional also and timing also.
Even digital analog power also separation, that is also important.
Yeah, exactly. So that's where the mixed signal verification comes to play, because ultimately you have to functionally verify the whole thing, analog and digital together.
Yeah, what about the opportunities, sir?
Oh, like I said, immense opportunities. In India, all these chip designing houses, they are looking for, physical design engineers, ST engineers, they are looking for analog designers and analog layout engineers. Right now, I mean, we have open specs that we can fill because we don't have enough engineers.
Thank you, sir. Good afternoon, all. I am Dr. Mrinal Deshpande, Professor and Head, Marathwada Mitra Mandal College of Engineering. I first of all congratulate all the panel members. It was an excellent discussion. And before going in for my question, in line with the first two questions, I would like to inform that in Marathwada Mitra Mandal, we have a Center of Excellence and Innovation Incubation Center, wherein we provide all the support to the startups. We provide place and also related help, whatever is required. Right now, 33 startups are going on there, and most of them belong to our students and faculties. So related to my question, since semiconductor and nanotechnology are going hand in hand, what about EMI interference? Is it a good topic for research? What is the scope? And has already AI stepped into that? Thank you.
Maybe you can take.
I specifically don't come from that background, so I don't probably can put a lot of light on that. But what I can say in general, the type of questions what are coming up. So as we discussed, it's a huge field, and my philosophy, or if you personally ask me, it's like if you want to drive something, like somebody asked AMS if we want to do, or you're talking about EMI or any other technical topic. So I think there is enough scope for each and every individual in this room to drive that and make sure industry or whoever support mechanism you want to use for that will definitely come and help you. So in general, to probably summarize, and I'm sure we have a lot of questions on each and every topic which is very close to our hearts, or maybe you want to do some research in that area. In general, what I want to say is just make sure whatever you want to do has a potential to be sold. Like Kedar sir said, everybody wants to do something, but at the end of the day, somebody has to pay something for what you are bringing to the table. So if you answer that question, whatever I am doing is value to somebody, and somebody is willing to pay for that value, I think all other things, ecosystem or whatever, this platform will take care of that. So probably that's the question we have to answer ourselves, and I think then all other problems will take care of itself. Thank you.
Thank you.
Thank you. Thank you to our esteemed panelists for such an insightful and engaging discussion, and to our audience for their thoughtful participation. So meanwhile, I request our panel members to kindly take their seats in the front row, and we thank you once again for your valuable presence and contribution here. Due to time constraint, we are not taking the technical session and we will formally conclude the ceremony. I invite Dr. Vandana Patil, Senior Assistant Professor, to deliver the vote of thanks.
Thank you, ma'am. All the dignitaries on the dais, respected guests, distinguished speakers, faculty members, industry experts, and dear participants. Very good afternoon to all. I, Dr. Vandana Patil, deeply honored and privileged to propose vote of thanks on behalf of Semiconductor Engineering of D.Y. Patil International University. First, I would like to express my heartfelt gratitude to our honorable chief guest, Mr. Paul Sir, for gracing this occasion and sharing valuable insights that truly inspire to all of us. Thank you, sir. I extend my sincere thanks to our Honorable Vice Chancellor, Professor Manish Bhalla, sir, for his visionary leadership and motivating words. Thank you, sir. I would like to also express my deep gratitude to our respected Registrar, sir, for his constant support and encouragement in organizing such an impactful academic event. I would like to express my sincere thanks to Professor Madhavi Deshpande, Dean, Faculty of Non-Engineering, for her valuable support and encouragement. I would like to express my sincere gratitude to Professor Anupama Patil, Dean, Faculty of Engineering and Director of School of Engineering Management and Research, for her constant support, motivation, and for her inspiring welcome address that set the tone for the event. Thank you, ma'am. I would also like to thank Professor Priya Charles, Associate Director, SEMR, and Head Semiconductor Engineering, for her insightful briefing and for her dedicated efforts in organizing this summit. A special note of thanks to all our esteemed panel members for sharing their expertise during the panel discussion on the role of semiconductor in next generation technology. I would like to extend a special thank to Professor Ashwini sir. I would also like to acknowledge and thank our industry partners, especially the representative from Kent Semicon Private Limited, for their valuable presence and contribution. My sincere gratitude goes to all organizing committee members, faculty, staff, teaching, non-teaching staff members, student volunteer for smooth conduction of the summit. Also, our special thank goes to all participants, those who have joined us today. With this, I once again thank you everyone for their presence and contribution. Thank you all.
Thank you, ma'am. Once again, thank you all for being a part of this insightful and enriching symposium. Before we conclude, I request all the